This is a second short video related to the second week of the online course. In this video I will quickly show you how to use funsim. Doing so, I will actually show you how to use these about 14-15 different types of equations. So the very first one is a step function. So I click on an auxiliary variable, just a normal variable, and I'm going to call this, for instance, a step up. Going to the equation button, clicking on my variable, I can here include a function. And if you want to select one, you can immediately write, for instance, a step function here, or you can also select the step function from the list of common functions. Mind you, there are a whole lot of functions predefined in this program and in other programs, and you hardly need any of them. So in this case, let me scroll to the step function, and then you see that you need to specify the height. And in this case, for instance, let's say that's 1, and the step time at which we need to step up. For instance, at moment 10. So if I do that, and let me first check my settings. Okay, let's give this a name. Yeah, so let me correct my settings. Let's simulate until month 20. 0.125 is the time step, and integration method Ruinkuta auto. Now let me simulate this. So this is the step up. Then you indeed see that it steps up from 0 to 10 to 1 at moment 10. Now it's very useful to for instance, step up and step down. If I do that and I step down with 1 at moment 11, then let's see what we get if we do that. And I'll give this run a different name and I simulate again. Then here you go. You actually have, this allows you to turn something on and then turn it off again. The second function that I would like to introduce here is a ramp function. For instance, again, ramp up. And here again, I can choose the ramp function from my list of functions. And you see that you need to specify 3 things here. That is a slope, for instance, 0.5, a start time, let's say 5, and the finish time, let's say 15. So now we are going to ramp up between moment 5 until moment 15, and we do so with 0.5 per time step. So if I do this, then here we go. What you see is that we have a gradual increase from 5 to 15, and that is pretty different from the step function, which is very, very discrete. And mostly you don't like these very discrete functions in these types of models. Then the third function that I would like to introduce is actually a predefined function, which is time. Time is of course of the essence in such programs, so that's why it's predefined. And if you simulate it, well, there's really no surprise. I mean, time is just time, so it progresses as the program progresses. But it's a very useful thing to have time, for instance, if you want to add some seasonality. So let me see, add some seasonality. And if I use time as an argument to, for instance, a sine function, the sinus, then this will allow me to obtain some oscillatory pattern. So let me simulate this. There we go, an oscillatory pattern. Now, if this should be some seasonal effect, for instance, with a maximum of 100%, so that's 1, and a minimum of 0, and say this effect peaks right before the start of the year and somewhere in the middle of the year, then I need to transform this function. So your goniometry should be, let's say, at the point where you can change the sine function or the cosine function using some trial and error. So in this case, that would, for instance, mean that I would first like to raise it. So if I say +1, then what will happen is that I will be able to raise it where it actually oscillates between 2 and 0, but this is not good enough yet because I want it between 0 and 1. So what I could do is multiply by 0.5 or divide by 2. If I do that and give this simulation a different name, then there we go. Then we have our seasonality between 0 and 1. But hey, I still want it shifted, and I want, so say for instance, if I shift, do I have peaks around month 6 and 12? Yes, so that's fine. I just need to shift it, and if I shift it, I need to shift it, yeah, with one phase shift. So what I'm gonna do here, but this is really where trial and error kicks in, I'm going to go for pi plus pi divided by 2, and this should actually be good enough to get the seasonal pattern that I desire. Now you see we have too many oscillatory patterns here to really check whether this works nicely enough. So I go to my control panel and I kick out the runs that I do not need anymore. And then indeed I can just focus on my one graph, and you see that here that you get an oscillatory pattern with a peak around month 7 and 12. So this is actually what I wanted to have. Then the next function, the next two functions that I want to discuss are the minimum function and the maximum function. And the minimum just takes the minimum of two values or two functions, and the maximum function takes the maximum of two values. But for instance, if we want to also get some seasonal effect, just as we obtained it with our seasonality function, but we want it, well, let's say, to peak at more or less the same moments, but we would like to have a longer period in which nothing actually happens, so that is here at the bottom. Then what we could do as well is add a seasonality 2, and instead of using the function that I used in my seasonality 1, I could also go for a sinus of time. And let me immediately shift this thing, so that is plus 3.14 or pi divided by 2. So let's do this, simulate it, and let's test what we get. So I want to get rid of all the negative stuff here, and then we also have a peak at 12 or beginning of the year and somewhere in the middle of the year. Now the way in which I can do this is actually by setting a floor. Now, you set a floor with the max function, not the min function, but the max function, because then you're going to take the maximum value of that function or 0. And if you do this, and there you go. Then you also have a seasonal effect, but with longer periods where nothing actually really happens. Say for instance we do not want these large peaks, but we want to top it at 0.8, then what we can do is use a minimum function to actually set a ceiling. So if I go for a minimum function of this whole function that we already had, or 0.8, then if I do this, then you see that instead of having the full sinus wave here, you would actually top it at 0.8. So this would actually be what I want to obtain. Now, in order to just make it clearer, let me kick out 0.2, and then you see the behavior that we obtain. So that's the first part. In the next video, I'm going to shoot the remainder of the functions.